Okay, recently King RCT3 came up with this interesting coaster riddle. How it can be true that a coaster can go above a hill that's taller than the station just by gravity. Since I'm a physicist, it didn't take long until I came up with this solution to the problem. But what does it mean and how did I came up with this? So let's first rebuild the thing and let's just play around with it a little bit, which will reveal an easy first answer. In this example you have two trains, while one train can make it over the hill and the other can't. Okay. So obviously in this example one train was longer than the other train. But what's the secret behind it? Why couldn't a shorter train make it over the hill? There's a quite intuitive insight into this problem. If you take the average of all the locations of the individual cars of the train, you see that the result moves downwards. So this moves more and more down the longer our train is. This is just the center of mass, so the center of mass always stays below the maximum train height. We can also test this in the simulator. So as the train starts moving, it goes downward and then up again. But now let's have a very close look. If you compare it to the starting point, you see that it's definitely below the starting point when the train makes it over the hill. So this was a very easy answer, also other people came up with. Let's just have another view on this problem in a moment, but we need some a little bit more different toy to play around with first. Okay, I admit it was a little bit more theoretical, but it's perfect to collect some data we will analyze now. And then we can finally build our theory, which we can then use to find an answer to how tall we can make it in the end. So let's have a little bit more abstract view on this thing. We have basically two heights we want to care about. And a simple concept associated with heights is something called potential energy. So at a starting point, each car of this train has some potential energy associated with it. But since we deal with a train, which is a chain of linked masses, we have to care about some of all these masses, which give us the potential energy of the whole train. So I set up a script in NoLimits to collect all the energy data. And I did it in such a way that we can now see the energy of the first car during the process. And on the right hand plot for the whole train. So this is just the sum of each individual car. Now let's speed this up a little bit and look how it develops. So the first thing we can note here is that this train still moves after it ended. This is because the energy never goes fully back to where it started at. And that the train still has some kinetic energy is just another word for saying it still moves. Now let's have a little bit more closer look at each individual phase. Right at the beginning, the first car loses all its potential energy and this contributes to the whole car energy. But since we are dealing with a train, the other cars that follow also constantly add some energy to the whole train. In the plots, this is shown as some linear increase of the energy level. And note, the car 1 energy still increases while its potential energy does not change anymore. When the train reaches the bottom of the first valley, nothing is there that can still add energy to the train, and it also shows in the plot as some constant line. So as the first car starts to climb, we can see that its potential energy now gets some constant and rapid increase. Since more and more cars starts to do this, the overall train energy starts to decrease more and more rapidly. So if you take care of the different scales of the plot, you see that the car 1 energy loss is much smaller than the energy of the train. So with other words, the train pushed itself over the top. Now the first car already started to give some energy back to the train. But we have more cars that climb up this hill, though the energy in total still decreases. This decrease though gets slower and slower, since the energy levels of the cars that climb up and go down get smaller and smaller. So this is also a curved decrease. And finally the train reached a state where each level of the hill cancelled out. So there's no change in energy and it just stays constant. Okay, so we have analyzed the problem. Now let's develop a theory. For this we don't need the individual train energy diagram anymore, and we first get rid of all the numbers. So what we want now is some expression for the energy the train gained in the valley by the loss of height. And we also need some expression for the loss of height on this little bump there. Let's simplify the train a little bit. Instead of caring about a sum of individual mass points, we can approximate it as a flexible mass line. This will turn sums into integrals in the calculations. Now let's also simplify the rail a little bit. We can approximate the hills by rectangles to get rid of complicated curves. The mass of the train is now some mass density multiplied by the length of the train. And this mass multiplied by the gravity and the height it dropped down is just the energy it received in the valley. So as the train starts to move up, the amount of masses that contribute to the energy loss increases constantly. This is why we would have to sum, or in our simplification integrate, the mass contributions. So math tells us the solution, we can note somewhere and do the other part. From the graph, for example, we can see that this is just a constant increase minus the exact opposite of the climb we have to integrate. When we calculate and simplify the solution, we see that this part is exactly the same as the other part. So we just have to take the climbing result 2 times, for example, to get the total energy loss of the second hill. So the key is now that this loss of energy must be smaller than the energy that the train gained when it left the station. After putting our noted results in and doing some simplification, we end up with the result I came up with. We can now check if this is true for our extreme coaster example, and yes, indeed this holds. And you will see it will also approximately hold for the more realistic examples. Okay, so there's one final question left, and I went through a little bit of more math and then I came up with a solution for this as well. So let's just pimp the coaster a little bit and see if it still works. I hope it was a little bit of fun to see how one can dive insanely deep into this riddle. And now just enjoy the final test run of the coaster. See you soon!